Yeah, hi. That's another quick article. Uh, I was writing about things, so every now and then I have to also read about things. So I stumbled across this article. Why does ice float on water? Normally, solids are more dense than liquids, so why is ice the exception? That's BBC Science Focus magazine. So probably English. Perhaps a cold, refreshing drink on a hot day would look so appealing if the ice cubes dropped like a stone to the bottom of the glass. But why does ice float on water? In fact, why does anything float at all? What makes something float? An object less dense than water will float. We can explain this phenomena with the help of a theory called Archimedes' principle. Before you carry on, we should warn you the following explanation will contain a lot of maths. As you have probably learned, I don't like too much math. I really like pictures and, how to say, things somehow to grasp. You can read the whole article if you want to. There's a whole lot of math, some pictures, and if you scroll down, you stumble across this crystal lattice. A material can form states of matter which differ only by the way the particles are arranged. Hmm. In a solid, the molecules pack themselves tightly together into a neat, orderly repeating pattern called the crystal lattice. When you start to heat a solid, its molecules gain energy and vibrate more strongly around their positions. Eventually, they gain enough energy that they can no longer be held in place and they break free of the lattice. This is a liquid. The molecules are free to move around but generally stay fairly close together. If you continue heating it, eventually the molecules will break free from each other entirely and form gas. And if the gas is heated, it is plasma. As the material goes through each phase, it becomes less dense. So now, why is ice less dense than water? If solids are denser than liquids, why does ice float on water? Because water is a special case. The molecules in water are affected by a phenomena known as hydrogen bonding. The water molecule is a V-shaped molecule made up of one oxygen atom in the center with a hydrogen atom on each side. The molecule is held together by covalent bonds, when two atoms share a pair, which is when two atoms share a pair of electrons. Blah. However, the oxygen atom pulls on these negatively charged electrons much more strongly than the hydrogen atoms can. No math included in this explanation, just as a side note. As a result, the electrons tend to hover closer to the oxygen atom than either of the hydrogen atoms. This leaves the molecules as a whole with a slight negative charge around the oxygen end and a slight positive charge around the hydrogen end. Since opposites attract, the slight charges on different molecules interact with each other. These interactions are called hydrogen bonds, which technically speaking aren't bonds at all. In liquid form, as the molecules move around, hydrogen bonds form and break over and over, and the molecules can slip past each other. However, as the water cools down, it starts to form into its crystal lattice structure. While the molecules want to form hydrogen bonds between the slight positive and negative charge, the same charges repel each other, stopping the molecules from getting too close. The result is a structure that is slightly less dense than liquid water. So, what makes ice float is basically the repellent force or the repellent reaction of similarly charged little things called atoms in the water. It's electrical. The whole thing is electrical in nature. The repellence keeps the gap in order to make it more spacious. There's also air in those gaps. That's why it's floating. Total, totally electrical. You can check out the math if you get it. But for me, this explanation is so much simpler to understand. Everybody knows how a magnet works. And again, this goes into the same what Gerard Pollack is explaining about easy water, hexagonal diachotron structures. If you, what is it, Jupiter, which has storms on its pole with exactly the same shape. Because also this planet's weather is electric in nature. Yes, I leave it here. You don't need math to understand nature. Probably you need it to explain it, but you don't need it to understand. I don't know. I leave it here. I just think it's really intriguing, all the things. There's, how to put it? When I'm reading these things, I'm always waiting it like, does it make sense? Does it fit into the electric universe paradigm? How to put it, Or does it not? Is there another rabbit hole to go down in order to figure out how things really work? And I have to say, there's no contradiction until now, at least, what I came up with. Not even the glacier being volcano theory is contradictive to the electric universe theory, which is really interesting. There are many people who understand much more about these things, can explain them much more better because they're educated. But as far as I was thinking about, for example, like that's the reason why I was reading that, because I am writing about glaciers. Learning by doing, learning by writing, learning by learning about learning. Yeah, it's really, really interesting. But I'll leave you here. Uh, Read the math if you want to. But for me, like just this simple explanation of charges, different kind of charges, and the repellence of magnetic forces and the attraction of magnetic forces. It's really, really interesting and really nice. It's simple, basically. You don't have to invent anything. It's like all around us, the patterns everywhere. You just have to once to figure out how to see them, where to see them, and like what you are looking for. What kind of patterns are those which are so plentiful in average in everyday life? That's really, really interesting. But I'll leave you here. Thanks. Bye.